Okay, welcome back. It looks like we're ready to go into some damped motion here. Again, make sure you put that P in there. So free damped motion. So we're still not putting an external force on it, but we are now going to include friction. So our equation, we have mx double prime plus ax, where a is your coefficient of friction, and plus ax prime plus kx equals 0. Again, we divide through by the mass, and we take our lambda to be root k over m, so that's the same thing we did for damped motion. And then we define this number b to be a over 2m, and that's just to make the numbers look nice eventually. So this makes it into x double prime plus 2b x prime plus lambda squared x equals 0. Main thing to remember is the lambda squared is the term that deals with the spring constant, and the b is what deals with the friction. Granted, they're adjusted, but we'll have to remember that bigger lambda means a stiffer spring, and a bigger b means more friction as long as the mass is kept constant. So our characteristic equation for that is m squared plus 2bm plus lambda squared equals 0. We pull out quadratic formula for the answer. So we get negative 2b. It's a little odd because we have 2b rather than just plain b. And then plus or minus, again, 2b quantity squared is 4b squared minus 4 lambda squared. The nice thing is we could pull the 4 out of the square root, and everything cancels with the 2 in the denominator. And that's the reason we did the substitutions. It makes this look pretty nice. So we have m is opposite of b plus or minus b squared of b squared minus lambda squared. Now, it depends upon what this term is as to what kind of motion we're going to get. So there's 3 cases here. This term can be a positive thing inside the square root. We could have a 0 inside the square root, in which case you have a double root. Or we could have a negative number inside the square root. So let's look at those 3 cases separately. So case 1, that means b squared minus lambda squared is greater than 0. Now, again, since b and lambda are positive numbers, that means b is greater than lambda. Now again, b represents friction. Lambda has to do with the stiffness of the spring. So in this case, we have a lot of friction compared to the spring's restoring force. So this is a high friction situation. And so this is called over-damped. So in an over-damped case, what we get is we get x of t. It's going to be C1 e to the minus b plus root b squared minus lambda squared t plus C2 e to the minus b minus root b squared minus lambda squared t. Because those are 2 real roots. Now, because we have b squared minus lambda squared, this thing inside the squared is going to be less than b squared. So the squared is going to be less than b. So this is still going to be a negative number. So we have e to a negative number times t, e to a different negative number times t. So both of these are going to be exponentially decaying out. Okay. Depending upon the values of C1 and C2, you theoretically could go through the equilibrium once, but it's going to ooze back. So in terms of your motion, if we have our equilibrium here at 0, this thing is just going to sort of ooze down toward equilibrium. Maybe it comes up once and comes back through, but basically this is just an exponential decay of motion. There's no oscillation whatsoever here. Okay, so overdamped means you've put so much friction in the system that it's not going to oscillate at all. It's just going to ooze back toward equilibrium. Okay, the next case is where b equals lambda. Sorry, lowercase b there. Well, in this case, we have a double root of m equals opposite of b. So we get x of t. It's going to be c1 e to the minus bt plus c2 t e to the minus bt. Again, sort of looks encouraging because this is decaying off, but we've got instead of t here, so that's growing. However, L'Hopital's rule tells us that that's still going to go to 0. So since it's a negative exponential, it's going to win out over the linear growth of t. So it's still going to go to 0. So this one it sort of almost wants to oscillate, but can't. And you can actually show in this case that at most it can hit equilibrium twice. Okay, so again, it's not going to look terribly different from case 1, but it might go through equilibrium and come back, but it's still not going to quite do it. The case we're really interested in, and the one that's actually does something that's interesting to watch, is when b is less than lambda. And in this case, if we go back to our solution here, this is b plus or minus, and then we can put an I times the square root of lambda squared minus b squared. So we factor the negative 1 out. So now what's interesting here is you get x of t is going to be e to the minus bt times c1 sine of root lambda squared minus b squared times t plus c2 cosine square root of lambda squared minus b squared t. Now, this part is periodic. However, it is decaying, so it's not a true periodic motion in the sense that it doesn't return to the exact same wave each time. Each time the wave is diminishing because of that e to the minus bt out there. So when we talk about this, I'll often just use the word period and frequency, but really it is what's called a quasi-period and a quasi-frequency because in reality it's not truly returning back to the exact same value. So our frequency and our period, well, this is 2 pi over square root of lambda squared minus b squared, and of course the reciprocal here. Now, if you think about what's happening here, again, b is representing our friction term. So when b is 0, we get the exact same formulas as we had for the undamped case, because this becomes a sine of lambda t, a cosine of lambda t, and e to the 0 t is just 1. However, when we have this damping term out here, we get this exponential decay here. Our period ends up being longer because we take lambda squared and we subtract the b squared down here, so we have a smaller number in the denominator, which makes the fraction bigger, so it takes longer to get through a cycle, which makes sense, or the number of cycles per second goes down. Okay, so that's frequency. So frequency, again, is going to go down. So in terms of notes, you see this with the human voice. If we decrease friction by, say, inhaling helium, what happens is your frequency goes up. There are gases, sulfur hexafluoride being one of them, that are actually more dense than air, that it increases the friction on the vocal cords, and then you sound like Darth Vader when you do that. That's not commonly available, though. Helium, though, is. Okay, so we see that in common experience. Okay, Well, the amplitude, though, is changing. So our amplitude, it's called a time-varying amplitude, that's going to be e to the minus bt times the square root of c1 squared plus c2 squared. So notice the amplitude is dying off here. Okay, so there's really not a lot in this section. The only problem you'll see when you look at the examples I'll put out is sometimes the algebra in these gets a little bit messy because obviously given initial conditions, solving C1, C2 can be a little bit messy. Okay, so again, this is a fairly short section, but it does point out what's happening here is that we're getting a change in frequency by introducing friction. The amount of change depends upon how much friction we add. And then we want to look at force motion. And that's where it's going to be the most interesting part, because what happens if the period of the force we're putting in is very close to this quasi-period for the natural motion? And we'll get to a phenomenon called resonance. And it can be a good thing or a bad thing depending on what you're trying to do. So in a speaker, you're creating resonance to make noise. Obviously, in many cases, the resonance causes things to fall apart. So that will be section 5.4. And that one's going to probably be the algebraically messiest one. The nice thing is it's not a difficult concept, but it is somewhat messy to derive. Thankfully, you don't have to rederive it. But we want to look at what are the conditions necessary to get resonance. It turns out when you have a damped system, even if it's underdamped like this, okay, so you have overdamped, critically damped, and underdamped. Even in an underdamped system, it's not always possible to get resonance. Okay, so if you're a Mythbusters fan, when they did Breaks That Bridge, they created something that they could never get resonance in. And we want to look at the relationships that have to exist between the lambda and the b in order for us to get some type of resonance phenomena. Okay, so that's what we're going to be doing in section 5.4, but that will wait till next time. Hope all is going well and you're all staying healthy. And we're almost at the end of the semester, so we've got a couple more sections, and then we will be ready to start prepping for a final. Take care. Bye.